In this lecture, we will talk about electroanalytical techniques, which includes variety of techniques based on electrolysis such as amperometry, polarography, voltammetry and many related techniques. Today, we will talk about the simple technique polarography, and I will discuss in the introduction how this technique was discovered and the working electrode which is used in this technique. It is basically dropping mercury electrode. Then the information obtained is known as polarogram, which is current potential curve. Then we will talk about limiting current, diffusion current and Ilkovic equation, which is the basis of determination by using polarography. There are two types of reductions which are reversible and irreversible systems. So, we will talk in brief about these systems. Then to summarize, we will talk about applications of polarography in industrial chemistry. Polarography was first electrochemical analytical technique which was discovered by late Professor Jaroslav Hirovsky, who is known as father of the electroanalytical methods, and the technique was discovered in 1923. Professor Hirovsky was working for his PhD in Czechoslovakia and he was awarded Nobel Prize in 1959 for his distinguished work in the field of polarography. This is the first polarograph which was used by Professor Hirovsky, and you can see here the electrode which is dropping mercury electrode. We will talk about it in detail in few minutes. Polarography can be classified as a subclass of voltammetry which deals with the current potential relation in an electrolytic cell involving a dropping mercury electrode as the working electrode. Now, the use of dropping mercury electrode distinguish polarography from voltammetry, where solid electrodes are used, which may be metallic electrodes or carbon surfaces, whereas in polarography always dropping mercury electrode is used as the working electrode. It has been employed for both qualitative and quantitative analysis in the normal concentration range of 10 raised to the power minus 3 to 10 raised to the power minus 5 molar and possesses limited sensitivity. Now, if we look the uses of polarographic technique, we can use it in different branches of chemistry as well as in pharmacy. In inorganic chemistry, we can use it for the analysis of inorganic metal lines, complex formation and so on. In organic chemistry, we can use it for the detection of large number of organic compounds. In physical chemistry, we can use this technique for the determination of diffusion coefficient, hydration of ions, pKa, kinetics of a reaction, etc. And in pharmacy and agriculture, we can use this technique for estimation of large number of drugs for clinical analysis and for detection of some diseases. Now, if we look the setup, it consists of a cell which contains the solution being studied. Here you can see we have a cell which possesses 3 electrodes. One is counter electrode, which is normally platinum, the reference electrode, which may be a calomel electrode or silver chloride electrode, and the dropping mercury electrode, which possess a glass capillary having a very fine bore, which is connected through a PVC tube or rubber tube with the help of reservoir of mercury. We fill mercury in the reservoir, which flows through the capillary under gravitational force, and therefore, the tiny drops of mercury flows continuously from the capillary. The working electrode is always dropping mercury electrode in the case of polarography, as I told you, whereas this electrode is replaced by solid electrodes in the case of voltammetry. A stable reference electrode, usually a calomel or silver chloride electrode, is used to measure the potential with respect to working electrode. Now, this is an enlarged version of dropping mercury electrode. Here you can see a conventional DME, that is dropping mercury electrode, consists of a capillary having very small internal diameter. As you can see here, when you connect it through PVC tube with the help of mercury pool, the mercury flows under gravitational force through the capillary and the small drops falls from the surface of this capillary. However, a precaution is needed here that the mercury which is used should be triple distilled, otherwise the impurities of the mercury will block the capillary and there will be no flow of mercury. The upper end of the capillary is attached to a rubber or PVC tube containing a column of mercury which is electrically connected to the external circuit, and the tip of the capillary is immersed in the solution being analyzed. Under these conditions, mercury flows through the capillary and forms a droplet at the tip, and the droplet then falls, stirring the solution to some extent, and another drop is born to start the cycle again, which means always a fresh surface of mercury is available at the tip of the capillary. The length of the capillary is so selected that the drop time falls in the range of 3 to 5 seconds. The drop rate can also be controlled by adjusting the height of the mercury reservoir. At higher height, the pressure is high and thus drop rate is large, thereby giving a small drop time. Therefore, if we increase the height of the reservoir, the drop time becomes small. The drops start falling at a faster rate. Now, the question comes, why we are using DME or why we are replacing solid electrode by a dropping mercury electrode. The first advantage is that the surface is continuously and reproducibly renewed. A reproducible average current is produced instantly on changing the applied potential. This is because the magnitude of the current depends on the size of the drop. The third advantage is that mercury has a large over potential for hydrogen formation, which allows the reduction of many species in acid solution, which means we get a large available window for the reduction of variety of compounds. However, there is disadvantage of mercury is that the mercury is highly toxic, as we know, and therefore, it should be very carefully handled and its vapors should not be inhaled. Its use has been restricted for the determination of reducible or easily oxidizable species, as mercury itself undergoes oxidation at about 0.4 volt, and therefore, DME is not a very good technique for carrying out oxidation studies, and therefore, polarographic technique is widely used for carrying out reduction studies. You can see that mercury easily undergoes oxidation to give mercurocyanins and 2 electrons are evolved. Now, if we see the change in potential with respect to time, we can see that a linear relation is followed in polarography and I, that is the current, is measured continuously. This is known as linear voltage waveform used in polarography. In manual instruments, we change potential ourselves and with time this potential increases. Whereas in the recording units, the motor driven change in potential takes place and the rate with which this changes may vary from 2 to 5 millivolt per second. This is the simple voltage waveform used. When we monitor change in current with change in potential, the first curve we are considering here is the lower curve B, which is observed when there is no electroactive species is present in the solution. And if an electroactive species is present, we get a curve which is similar to A. Here we can call it as S-shape curve. This curve has two important characteristics. First is known as current, which you can see here is monitored as an average of this current and the background current, which is B. If we get the distance of these two, we get corresponding current. Whereas, if we divide this current into two equal halves and draw a third line parallel to the baseline and the top line, and the point at which it cuts the curve is known as half wave potential, commonly represented as E half. Now, you can ask why there is fluctuation at the top of this curve. The current is not constant, but there is continuous fluctuation. This fluctuation in the curve occurs because when the drop starts growing, it reaches to a maximum size. At that point, the current is maximum, and when the drop falls from the capillary, the current becomes minimum. And therefore, we can see here zigzag pattern. The current at the maximum represents when the size of the drop is maximum, whereas the current at the bottom here indicates when the size of the drop is minimum, that is when the drop just breaks from the capillary. At small applied potentials, only a residual current flows in the cell, which is caused by the reduction of trace impurities in the sample solution and by charging of the mercury electrode. You can see here the current, which is the minimum current, it is known as residual current. Here you can see again we have I average, where we have taken the intermediate or the average current at the top. This is known as total I average, and this is known as I maximum when we are considering the maximum current. When the size of the drop is maximum, it is known as I max. At the decomposition potential, the reduction of the electroactive species is initiated. At this point, this is known as decomposition potential when the current starts increasing. As I told you, when we divide this I average and draw a third line perpendicular to the limiting current and the base current, and the point at which it intersects the curve is known as half wave potential or E half. The current after decomposition potential starts increasing with the applied potential, and it levels off when the maximum number of ions reduce at the surface of drop. The difference between the limiting current and residual current is known as the diffusion current. The potential at which current reaches half of its limiting value is known as half wave potential, as I told you, and it is represented by E half. Now, if we consider half wave potential of some common metal ions in KCl, for cadmium 2 plus it is 0.62 volt, for cobalt it is 1.20, for zinc it is 1 volt, and for iron 2 it is 1.30. All these potentials are negative, which represents that these metal ions are undergoing reduction. More than one metal ions can also be determined simultaneously, but the condition is that the E half values should at least be 100 millivolt apart. If the half wave values are less than 100 millivolt apart, then the two wave merges and it is difficult to determine them simultaneously. Now, let us come to basis of polarographic analysis. The diffusion current is directly related to the concentration of the solution. The more concentrated the solution is, the greater will be the rate at which ions will reach the electrode surface, and thus greater will be the diffusion current that results from their reduction. The direct proportionality between the diffusion current and the concentration of the solution is the basis of the quantitative polarographic analysis. Whereas, under a set of defined experimental conditions, each ion has its own characteristic half wave potential, which is the basis of qualitative polarographic analysis. The limiting current is the total current measured at a potential on the plateau of a polarographic wave. Plateau means when the current becomes almost constant or the reduction occurs at the maximum concentration of the ions which are reaching at the surface of mercury drop. It is basically the sum of three components: the residual current, the migration current, and the diffusion current. First, let us discuss residual current. Residual currents may be regarded as the sum of two components, that is, a current which is consumed in charging the drop and the electrical double layer around the surface. A Faraday current which is consumed by the reduction of traces of impurities or dissolved oxygen, which means the residual current is due to two components. First, the current which is required to charge the drop, and second, the traces of impurities which are present may also undergo reduction, and this leads to residual current. The Faraday current can be minimized by using pure reagents and by bubbling nitrogen before recording a polarigram in order to remove the dissolved oxygen. The reduction of dissolved oxygen results in two waves because of the following reactions. Say, in acidic medium, oxygen takes 2 proton and 2 electrons, giving hydrogen peroxide. Oxygen takes 2 molecules of water and 2 electrons, giving hydrogen peroxide and 2 OH minus, and the second reaction occurs in alkaline or slightly neutral solution. Now, you can see here, when we record polarigram without bubbling nitrogen, the oxygen present undergoes reduction in two well defined waves. You can see here, oxygen is taking 2 proton, 2 electron, giving H2O2, whereas the second reduction wave is because of oxygen taking 4 H plus 4 electron, giving 2 molecules of water. The E half in the acidic medium is minus 0.05 volt with respect to saturated calomel electrode. So, you can see here around minus 0.05 volt we have the first wave. The reduction of dissolved oxygen results in two waves. So, in acidic medium we have seen H2O2 plus 2H plus 2 electron, giving 2 H2O2. This reaction occurs in the second wave. Then in alkaline or neutral solution, the reaction takes place where hydrogen peroxide takes 2 electron to give 2 OH minus. The reduction potential for this reaction is minus 0.9 volt with respect to saturated calomel electrode, and you can see here two well defined waves. Whereas, if we bubble nitrogen, remove the dissolved oxygen from the solution, we can see the lower curve, which is oxygen free solution, is obtained, and these two waves are not obtained. Therefore, the primary requirement of polarography is that we must bubble nitrogen to remove dissolved oxygen, otherwise these two waves will always interfere with the reduction of our species. These two waves can thus interfere with the waves of other electroactive species, and it is therefore necessary to purge the solution with nitrogen. Then comes the migration current. In addition to the diffusive force due to the concentration gradient around the electrode, there is also an electrical force which affects the rate at which ions reach the electrode surface. The portion of the total current that originates because of the migration of the ions due to electrostatic attraction is known as migration current. The migration current depends on several factors like transference number, charge of the ion, size of the ion, and therefore, by taking fairly high concentration of a supporting electrolyte, the transference number can be decreased virtually to 0, and thus the migration current can be practically eliminated by eliminating the electrostatic attraction between the ions and electrode. Diffusion current is the current that arises because of reduction of ions which have reached electrode surface due to the concentration gradient. The concentration of ions at the electrode surface is virtually 0, whereas its concentration is higher in the solution, and therefore, the ions flow from higher concentration to the lower concentration. The relation between the concentration of the ions and the diffusion current can be expressed in a equation derived by the scientist Ilkovic, which says the instantaneous current at any time during the drop life can be expressed using the relation I d is equal to 706 n d half m to the power 2 by 3 t raised to the power 1 by 6 multiplied by c, where n is the number of electrons involved in reduction, d is the diffusion coefficient in centimeter square per second, m rate at which mercury flows, which is expressed in milligram per second, c is the concentration of solution in moles per liter, and t is the drop time in seconds. In the last slide, the expression for instantaneous current is seen, while mean current during the drop life is a more appropriate quantity. Mean current is related to instantaneous current by the relation I d is equal to 6 by 7 I d instantaneous. Thereby, we can write an expression which is known as Ilkovic equation I d is equal to 607 n d half m raised to the power 2 by 3 t raised to the power 1 by 6 c. The above given equation is based on the assumption that the drop is spherical, but in actual, when the size of the drop grows, the sphere becomes elongated. Scientist Lingin modified this equation by putting an additional term to make correction for spherical to elongated term, or you can say just to cover the change in the size of the drop 1 plus 39 d raised to the power 1 by 6 t raised to the power 1 by 6 divided by m raised to the power 1 by 3. For more accurate measurements, Lingin equation should be used. However, for most of the general applications, Ilkovic equation is sufficient and provide good results. Now, the question comes to consider the factors which affect diffusion current. The first is effect of drop time. There is a condition that Ilkovic equation holds good only if the drop time is in the range of about 2 to 5 seconds. If drop time is less than 2 seconds, it will result in stirring of the solution, which will result in mechanical convection, and thus changed results are observed. Now, if the drop time is more than 5 seconds, the ions will approach much slowly, and thus unstable parallelogram will be obtained. Then comes effect of concentration. Diffusion current is directly proportional to the concentration of the analyte. As the concentration of the solution increases, the greater will be the rate at which ions will reach to the electrode surface, and thus greater will be the diffusion current that results from their reduction. Then height of mercury reservoir also plays an important role, because this change in height changes the value of m raised to the power 2 by 3 and t raised to the power 1 by 6. There is no direct dependence of diffusion current on height as per the Ilkovic equation, but since the term m raised to the power 2 by 3 t raised to the power 1 by 6 is directly dependent on the height of mercury reservoir, and therefore, the diffusion current is also dependent on the height of mercury reservoir. I d is proportional to m raised to the power 2 by 3 t raised to the power 1 by 6. As higher the height, higher will be the rate at which mercury flows, and thus smaller will be the drop time. Therefore, in terms of height, we can say m is directly proportional to h, and h is inversely proportional to the T, which is drop time. Now, if we write in terms of H, ID is proportional to H raised to the power 2 by 3 and H raised to the power minus 1 by 6, which means ID is proportional to H raised to the power 1 by 2, which means that diffusion current is directly proportional to under root H. If we carry out an experiment at different heights of mercury reservoir and plot the current against under root H, we will get a straight line proving that the current is diffusion controlled. Then effect of temperature. The temperature coefficient of the diffusion current constant is usually about plus minus 1.3% per degree, which includes the effect of temperature on density, mass, drop time, concentration and the numerical constant in Ilkovic equation. Temperature coefficient is given by an equation. Temperature coefficient is equal to 2.303 divided by delta T log I2 by I1, where I1 and I2 are the currents at temperature T1 and T2. Delta T is the difference of temperature at which current is I2 and I1. If temperature coefficient has a value less than 0.02, that is 2%, the current is diffusion controlled, and if it is much greater, then the current is controlled by some other factors like adsorption, catalyst and so on. Let us try a question. Calculate temperature coefficient for a metal ion which exhibited current as 5 and 10 microampere at 25 and 60 degrees respectively. The solution is, we know temperature coefficient is equal to 2.303, 60 minus 25 are the temperature difference log 10 by 5. This comes as 2.303 by 35 multiplied by log 2 and the result is 0.019, and if we change it percentage per degree, this comes out as 1.9%. As temperature coefficient is less than 2%, we can conclude that reduction is diffusion controlled. The solution composition also affects diffusion current. According to the Stokes-Einstein relation, the diffusion coefficient of a spherical particle is much larger than a solvated molecule. It is inversely proportional to the viscosity eta of the solution, and therefore, ID is equal to 1 by eta raised to the power 1 by 2, and therefore, the viscosity of the medium also plays an important role in diffusion current. Now, let us discuss about reversible system. Two most common type of reactions at a dropping mercury electrode are Mn plus, that is metal having N positive charge is taking N electron at the surface of mercury to give MHg, that is metal formed is making amalgam with mercury. If these half reactions are reversible, then the potential of DME is governed by the Nernst equation, that is E is equal to E0 minus 0.0591 divided by N log M Hg, that is metal amalgam, divided by Mn plus 0, which indicates the concentration of metal ion at the surface of mercury, where Mn plus 0 is the concentration of Mn plus at the surface of electrode and Mhg is the concentration of metal in amalgam. After solving for various parameters, we get an equation E is equal to E half minus 0.059 divided by n log I divided by ID minus I, where ID is the total diffusion current and I is the current at potential E. Thus, using the derived equation, we can say the slope of log I over ID minus I versus E for a reduction should be a straight line with the slope 0.0591 divided by n. The intercept of this straight line should be E half, and this is the fundamental criteria of polarographic reversibility. There are many techniques which have been derived from polarography and are more sensitive in comparison to normal polarography. The first one is pulse polarography. Pulse polarographic techniques are measurements which try to minimize the background capacitive contribution to the current by eliminating the continuously varying potential ramp and replacing it with a series of potential steps of short duration. We have two types of pulse polarography. First one is normal pulse polarography and second one is differential pulse polarography. In normal pulse polarography, normally written as NPP, each potential step begins at the same value, that is a potential at which no Faradic electrochemistry occurs, and the amplitude of each subsequent step increases in small increments. When the mercury drop is dislodged from the capillary by a drop knocker at accurately timed intervals, the potential is returned to the initial value in preparation for a new step. You can see here we are changing potential with respect to time. Here we are applying a pulse, you can see here, and the amplitude of the pulse is continuously increasing at successive drops. Then you can see here that the current is sampled during the last few milliseconds of the applied pulse. In the second case, differential pulse polarography, as the name indicates, we measure the difference. Here, differential pulse polarography is a technique which uses a series of discrete potential steps rather than a linear potential ramp to obtain the experimental polarigram. So, here you can see what we are doing. Here we are plotting potential with respect to time. So, at each drop we are applying a pulse, but we are not coming back to 0, and you can see here a linear ramp is superimposed with pulses. Now, here the duration of the pulse is about 40 millisecond or 50 to 100 millisecond, and the current is sampled 2 times, just before the application of the pulse and during last 20 millisecond of the pulse. The analytical current in this case is the difference between the current at the end of the step and the current before the step, and the limit of detection with differential pulse polarography are much lower in comparison to normal pulse or ordinary DC polarography. Here we can easily go up to 10 raised to the power minus 8 to 10 raised to the power minus 9 molar. Here you can see a differential pulse polarigram. Since we are plotting the change in current or the difference in current with applied potential, we get a peak in place of normal polarograms, which are S-shape polarograms. We can apply this technique for determination of trace elements like lead, cadmium, copper, iron, nickel, cobalt, aluminium, chromium, mercury in various industrial effluents. Determination of nitrate, nitrite, chloride, iodide, cyanide, oxygen during water quality analysis. Determination of numerous organic and toxic materials like surfactants, herbicides, pesticides, insecticides, nitro compounds, halogenous compounds and so on. We can also analyze tribodiagnostics of oils and lubricants using these techniques. So, in this lecture we have discussed about polarography, the use of working electrode which is DME, the polarigram obtained with two characteristics E half and ID, the limiting current, the use of Ilkovic equation which controls the current and reversible system. In the next lecture, we will discuss another electrochemical technique which is widely used in industry. It is amperometry. We will talk about various aspects of amperometry, how it can be utilized, what type of instrumentation is used and its application in industries.